We continue from the previous lecture. Okay, still remember what we discussed about this topic, this slide last time? What are the discussed issue on these topics? What we discussed? Okay, please be active, huh? Don't just wait for my answer. What we discussed? I just want to recap with you. What we discussed? No, remember. Lost somewhere in space. I'm sure most of you attended the class. So what we discussed? Huh? Edson? Correct. Yes. Thank you for the response. What's your name? What's your name? Huh? Sorry, I cannot remember all of you. Huh? Log Yuan Okay, thanks. What should I call you? Yuan Yeah. Okay, thank you, Yuan Okay, these are the discussed alternatives for VCM. Alternatives of what? Sorry, alternative what? Alternative method, alternative step, or alternative what? It is not only focused on the alternative methods. I mean process. Okay, it is not only alternative process to produce the VCM. It is alternative steps on how to fulfill the market demand of 800 million pounds per year. Okay, it is not only to retrofit your process or change your raw material. There are other ways. Okay, you can outsource. You can use the byproduct and you can purchase the raw material from other source. Okay. Now, last time we had discussed all the primitive design problem by using VCM as the example. So once you complete the first stage, then you can come up with the flowchart, process flow sheet. Okay, once you develop the flow sheet, then you can determine how you want to integrate your process. Okay, once you settle with the process integration, then you can move to part 2, the detailed process synthesis, where these two still interconnected. Okay, you can still go back to your part 1 to suit your part 2 process. Okay, so part 1, part 2, and part 1, part 2, this is your PDP1. PDP1 stage. Once you come out all with the heat exchanger network, the mass balance calculation, energy balance, identify your unit of, okay, have the basic process flow. Then in PDP2, you will do this, the design project, the design of equipment, sizing, everything. Then the economic analysis, safety part. Okay, part 3, part 4. Okay, now we have discussed part 1, part 2, and part 3. Now we move to the environmental protection, where these are the 5 major points in major environmental issues in design. Okay, for the design objective, you should focus in order to fulfill the environmental issue, to fulfill the environmental requirement. You should focus on your design objectives, constraint, and optimization. Okay, constraint here usually refers to the environmental regulations. Okay, let's say you have your product, but then your waste should meet standard A. So that is your constraint. So you should design your process, your waste treatment plant to meet the standard A. Okay, that is the constraint. Then handling the toxic waste. First of all, you need to identify what are your waste, what waste that you produce. There must be some waste. Okay. Then whether it is toxic or not. And then how you want to handle. If solid waste, toxic solid waste, what are the methods to handle it? If liquid toxic waste, so what are the methods? Gas, what to do? Okay. Then the reaction pathway. Reaction pathway to reduce the byproduct toxicity. Okay, this one focus on the byproduct. From the VCM process last time, the byproduct is HCl. Identify whether it is toxic. If toxic, how is the level of toxicity? And then how you can manage it. How you can design the storage system for that byproduct if you need to store it first. Okay. Then reducing and reusing the waste. How you can reduce and reuse your waste. Okay, let's say you have wastewater. Can the wastewater be reused? Can the wastewater be reduced? Okay, if you want to reduce, which part that you need to optimize? Then avoiding the non-routine events. Okay, basically here you will have, in the process, you will have your routine step. Then avoid the non-routine, because sometimes the non-routine one will cause some issue and some problems. Okay, so you must have your routine checkup, and then here it spell out like reduce the likelihood of accidents and spill through the reduction of transient phenomena, relying on operation at the nominal steady state. Okay, with reliable controllers and fault detection system. When you have your control system, so you should know how it can detect the faulties. Then if it detect, what you should do. What is the lower range, upper range? Okay, so within the range, you must have your normal range. If the reading go beyond the normal range, you need to start to check through already what happened to your process that it produced above normal range, not wait until the maximum limit. Okay. Now, from this VCM production plant, what are the waste that you can notice being produced from this plant? We know that Cl and ethane is the raw material. This is the feed. Okay, these are the products. VCM product. HCl is the byproduct. Now, what are the wastes produced? What are the waste produced? What are the waste produced? It doesn't show inside here, but there are waste. What are the waste produced? Huh? Byproduct is not considered as waste. There's byproduct. What are the waste? Apart from Cl, ethane, HCl, and the VCM, what are the wastes? Huh? Someone say something? What? Yes, wastewater from where? From utilities. Okay. Wastewater from the utilities. Other than that, impurities from chlorination. Okay, here, impurities from the chlorination. From the reactor. Okay, here it can be in solid form or liquid form. Okay, or it can be in sludge form. Other than that, product from pyrolysis furnace. Here. What are the possible products? Waste gas, correct. Okay, so here it occurs the combustion. Okay, it occurs combustion. So it will heat up the raw material over here, then it will produce waste gas. Okay, the gas here, it can be CO2, CO, syngas. It depends to the raw material that you use, that it use. Any more? Any more that you can observe? Those are the three main ways that I can observe, that we can observe. Okay, do you have any more other than these three? Refrigerant considered as a waste or not? It's part from the utilities as well. Refrigerant, cooling water, steam. Okay. Okay, so from here, from the five points over here, so you need to consider all these 5 points. What are the constraints? Meaning that what are the standards when this gas will be released from your plant? So if gas, what are the standard for CO2 from air pollution? Okay, there must be a standard. And then for the impurities, perhaps this is a sludge. What are the constraint? The Department of Environmental Standard. Okay, the wastewater standard A or standard B that you need to follow. It depends to your plant, where you build your plant. Okay. How to differentiate standard A and standard B? I'm sorry. I rephrased the question. When to use standard A or standard B? Depends on your plant location. Okay. Where should you refer to standard A? Where should you refer to standard B? Get out my questions. You set up your plant at one location. So how do you know which standard that you should refer to apply to your plant? Should you apply standard A or should you apply standard B? That one you need to look through. Okay, whether your plant is near to the water source to a settlement or not. It depends to the water source to the settlement. Which standard that you should refer. Okay, each standard has higher level, has higher requirement because it is if your plant closer to the residential area, water catchment. Okay, if your plant closer to your water catchment, either one of the standard you should follow. Okay, you should check on that. It is not simply you suka-suka to pick. I want to follow standard A. No, it's not. It won't work like that. DOE will come and check which standard that you should follow. Okay, can? Usually for your PDP, we will ask you on the waste treatment part, which standard that you follow. If your waste have gas, so what standard you follow? What are the limit that you should produce, release, the gas release? And then same goes to your FYP as well, final year project. If you are dealing with the waste treatment, you should know which standard that you are referring to. For example, you treat wastewater using adsorbent, for example. So until what limit that you want to treat? What standard you follow? If your plant producing minimum amount of pollutants, so why do you need to treat your wastewater? You don't need to treat anymore. So that's one of the problem statement also. Okay. Okay, any questions before we move? Can Now I want to share with you the example of disaster from the world. Disaster one is from Flixborough, 1974. Okay, where it released 50 tons of cyclohexane from its plant, okay, leading to releasing of vapor cloud and its detonation. It explodes because this is flammable. Okay, vapor cloud and it explodes. So total loss, 28 plant personnel. The staff lah, the workers. Okay, it is a highly reactive system with large inventory in plant. Okay, process involves 6 of 20-ton stirred tank reactors. The cause is because of the discharge caused by failure of the temporary pipe installed to replace the cracked reactor. Okay, here is the cracked reactor. They installed a temporary pipe. This pipe not able to contain the operating conditions, 10 bar, 150 degrees C. So it track and release the vapor cloud. Okay. Now the lesson learned is to develop process with low inventory, especially of flashing fluids. Okay. Then before modifying the process, carry out a systematic search for possible cause of problem. Okay, before you do it, find out what will happen. Pros and cons of the solution. Then construct modification to same standard as original plant. Okay, so the pipe that used as temporary pipe must have the same standard as the reactor. Because the reactor is designed to contain this temperature, 10 bar, 100 degrees C, this condition. So the pipe should also be able to sustain that condition. Okay, use blast resistant control rooms and carry out hazard analysis. Okay, so these are the pictures of the disaster. Now, this is the hazard analysis, the example. For the hazard, you need to do each of the instrument. Okay, each part of your process. Okay, so for example here, the valve for the air. Process parameters is the flow. Okay, then possible causes. What will happen if the valve fail? Okay, these list down the possible causes. What are the possible consequences? Okay, and what are the action required? And who should be respond to? Is it the engineer, the technician, or the operator? Okay, the person in charge. Okay, next is the Bhopal 1984. It is due to the water leakage into the storage tank, methyl isocyanate storage tank, leading to boiling and releasing of 25 tons of MIC vapor, toxic gas. Okay, and it kills more than 3,000 civilians, injuring 10,000 more. Okay. Now, gases is more, released gas is more dangerous than explosion because it can move with the wind. Okay. If explosion, perhaps it covers only certain kilometers. But if vapors, it moves with the winds. It can go so far. Okay. That's why it kills and injured thousands. Then the cause is because of the refrigeration system to cool the storage tank had been shut down. Scrubber was not immediately available and the flare was not in operation. Okay, flare is one of the options if you have gas, if you release waste gas. Flare is one of the options. Okay, why flare is one of the options? If you have toxic gas, toxic waste gas. Why do you think flare is one of the options? What do you think? What do you think? Okay, correct. Thank you. What's your name? Huh? Yanzhe. Okay, thank you, Yanzhe. Yes, flare, you combust the gas. So you will release CO2, H2O, and energy. Complete combustion. Your toxic waste gas can be the fuel to that combustion process. So from toxic, you only release CO2, H2O, and the energy. Okay, so it converts from the toxic gas into lesser toxic gas, CO2. You just need to control the concentration of the CO2. Okay, so somehow, some of the plant, flare is one of the options. You can also use scrubber. Okay, scrubber is one of the options as well to treat waste gas. Anyone from Kedah? From Kedah? Have you been through to Kedah? If you've been through to Kedah, there's a fertilizer plant in Kedah, Gurun, Kedah, Petronas Fertilizer. So if you pass through there at night, you can see the flare system. Okay, they use flare system to treat their waste gas. Okay, or if you are from Terengganu, I'm sure most of the plant over there, if you go through, you can see the flares. Even in JB, Johor, the plants. Okay, some of it, they use flare as the options. Okay. Now, the lesson learned over here is to avoid the use of hazardous materials, minimize the stock of hazardous materials. Perhaps you don't keep too much stocks of the hazardous materials. Okay, again, you should carry out the hazard analysis. In each plant, you should carry out this analysis. Train the operators not to ignore the unusual reading. Okay, this is what I meant if, let's say your reading system, for example, your reading system between, for example, the pressure, you set between 10 to 20 bar. Okay, the pressure. So the normal reading is 15. Normal reading is 15 bar. Every day you do checklist, the reading of the pressure is 15 bar. But if one day you do your morning check, morning walk, one of the pressure control system showed 17 bar. Okay, out of normal. Then you should go to that particular equipment, check what are the root cause. What caused the pressure to increase? Okay, you cannot wait when it goes to 20 bar. This is the maximum limit already. Okay, if it is out of norm, you should go and check what happened. What are the root cause? Okay, is there any pressure relief valve operating or not? Okay. Then the next is keep protective equipment in working order. Then control building near major hazard. Okay, next is the Challenger disaster, the spacecraft. Just 70 seconds after the launch, it kills few astronauts. Okay, this is a waste. It's not easy to become astronauts. Now, what happened? The cause is because of the O-ring. The O-ring is designed to separate the section of the rocket booster. Okay, the O-ring failed due to the cold temperature, in which the O-ring problem has been identified months before the disaster. But the management is not considering the concern of the engineers. Okay, so that's why it is important for you engineers to make sure the management understand the problem, because certain management, they don't want to understand the problems. They just want to reduce the cost, cut the cost in any way they can. So as engineer, facilities engineer, importantly, have to make sure the things is safe to be run, is safe to be operated. Okay. Okay. Again, carry out the hazard analysis apart from the rest. Okay, this hazard analysis, as you can see in the previous example just now, where is it? Here. Later on in your PDP, most of the semester I found out the groups is, I'm not saying all, some of it just copy paste from the groups, from the seniors, because you later on you will find out it will be quite similar. It's just the same practice. Control this, reduce this, increase this. It's just the same. But you need to know and understand what you write. Last time when I went to, I evaluated in UTM together with industry, as I mentioned earlier, the industry, they focus on the safety. They want to see what are the hazard analysis that you run, that you have done. And they ask one by one of each point. Okay, and you should understand what you are writing. Okay. Let's say over here, action required. Install flow meter and low flow alarm to alert operator. Okay, why you need to install this? How do you need to install it? Where do you need to install this? Okay, how to make sure the operator are aware of this? Okay, it is very important on the safety part. Replace and clean valve. When to know when you should replace or clean the valve? How to know? Okay, who will clean and replace the valve? Okay. Okay, so we are done those parts. Okay, last slide on the design safety. Techniques to prevent fires and explosion. Inerting, by use inert in your raw materials. Okay, addition of inert dilutant. Some of it, the inert will dilute your raw material, the highly toxic raw material. Okay, that one we will go in details in the next topic. So install the grounding device. Use explosion-proof equipment. Okay, ensure ventilation. Install sprinkler system. Okay, and you must have the relief device, like pressure relief device. Okay, then you should do the hazard identification and risk assessment. Okay, and all these things are. You take safety this semester, taken already. So that subject will help you in designing for safety chapter for your PDP. Okay, this one you can read through the common questions for the first part of your process. Now we move to a hierarchical approach. What does it mean by hierarchical approach? Hierarchy. Hierarchies. Arrange in order to the importance. Arrange in order to their importance. Okay. In process design, so you need to arrange what are the most important part first. You want to design a process. Let's say you have product VCM. So what comes first? You need to identify your raw materials. Right. So your raw materials, you need to identify, you need to select what are the alternatives of your materials. Then only you go to the process. Identify the process. Then identify your unit operation. Okay, there are steps. Okay, the most important decision in the process is the choice of which chemical synthesis or routes to produce the desired product. Then identify the alternative process. Like we did the example of the VCM. Okay, on the alternative part, is there any alternative for the raw materials? Okay, is there any alternative for the process? Okay. And then the conceptual design and the optimization. Necessary condition for any successful new process. After you finalize your synthesis, your routes, then only you come with your conceptual design and optimization. Okay, alternative routes may require different raw materials and may produce different byproducts. So these different byproducts, what you can do with it? Either you can sell it or you can reuse in your process. So these are the evaluation of alternative synthesis route. The cost, okay, the value of the byproduct, the complexity. Complexity here means any complex reaction involved or not, or any complex specific reactor that you need. Okay, or perhaps you need a specific catalyst to produce that product. Not common catalyst. So you need specific catalyst. Where can you get it? Is it easily purchased? Going home already. Okay, then how it impact the environment? Okay, so these are the design sequence. The 5 design sequence. So the first thing is you need to decide whether the process will be batch or continuous. Let me delete the blue color. Still not reaching your destination. Okay. First, to decide whether your process will be batch or continuous. Which one is the best for your process? Okay, then identify the input and output structure. Input and output structure is what is your feed, what is your product as a whole. Okay, not yet separated into few process yet. Okay, as a whole, feed product. Perhaps then, what do you have as your waste? Possible waste. In feed here, do you need any catalyst? Okay. Then identify and define the recycle structure. Do your process able to have recycle structure? Let's say you have wastewater. So you need to identify whether your wastewater can be treated and can be recycled. Okay, certain process, they just let go of the wastewater because perhaps the process need pure water. Instead of treating the wastewater, they can just take the supply from the state water supply. Okay, because sometimes the wastewater treatment costs a lot as well. Okay, so you need to consider the cost of treating the water and cost of paying from the state supply. Okay, you play around with the cost. And then identify and design the general structure of separation system, whether you need any filter or membrane, evaporator, any unit operation for separation. Okay, then identify and design the heat exchanger network or process energy recovery system. How many heat exchanger that you require? Can you optimize them or not? Okay. Okay, all this can be applied to existing process, which you want to do the retrofitting process or the new process. Okay. Okay, step 1. Remember, there are 5 steps. Okay, we will discuss in detail each of these steps. Okay, these 5 steps, all these 5 steps. So we discuss in details. Step 1, either your process, batch, or continuous. Which one to proceed? Let's say your process involves fermentation. So which one is better? If fermentation, batch, right? Fermentation works best on batch because you need some time for the process, for the mixture to be fermented, right? Okay, so we go point by point. Most chemical processes are described as continuous. Receive their raw materials feeds and ship their product to and from the plant, okay, from the transporter. The loading, unloading, and loading are done in batch manner. Okay, that one is also part of the process. Plants that operate continuously but feed or receive material from other process units within the plant that operate in batch mode, semi-batch. We call as semi-batch. Okay. Now, batch process. A finite quantity of product is made during a period of few hours or days. Okay, batch process. For example, your fermentation. You put in your mixture in the fermenter, wait for a few days or few hours for the solution to be fermented. Then at the end, you will have your product. Okay. For continuous, the feed is sent continuously to a series of equipment. Okay, with each piece usually performing in single unit op. So you have for continuous, you have in and out continuously. For batch, you have a certain duration. You also have fat batch, then batch product removal. Okay. Now, these are some of the factors to consider when deciding between batch and continuous. Okay, you must, be able to describe some of these factors. Okay, perhaps 5 factors from this. Okay, first one is the size. If your production or loading have bigger size, perhaps you need to do in a parallel continuous process or series continuous process. Okay, it depends to the size. Then batch accountability and product quality. How would it be? Okay, operational flexibility. Which one is more flexible to be operated, batch or continuous? Okay. Then standardized equipment for multiple products. Efficiency. Which one is more efficient, batch or continuous? Okay. And then the maintenance thing, the feedstock availability, the demand, okay, rate of reaction to product, equipment fouling, safety, and controllability. Okay, batch processing is probably the correct choice if the desired to produce small quantities, less than 500 ton per year. Okay, and then a variety of different products. Then using different feed material. But continuous, desired when you have large quantities, using a single or only few raw materials. That means the process is continuously working. You need to produce, maybe you need to produce a target 500 ton per year. That one small, 500 ton per week. So you must meet that amount per week continuously. So you need to arrange how much is your feed, how how is the rate, loading rate perhaps, okay, process rate. Then capital investment of batch system usually much lower because same equipment can be used for multiple unit ops and can be reconfigured easily for a wide variety of feeds. But operating labor costs and utility tend to be much higher. Okay. Any questions so far? Step 1, batch or continuous or both. Okay, depends on your process. Now step 2. The input and output structure of the process. Uses the stoic of the main reaction pathway to identify the feed and product chemicals. Okay, what do you understand the stoic of the main reaction pathway? Stoic of the main reaction. Stoichiometry. What can you understand from that statement? What can you understand from that statement? Uses the stoic. Anyone? Chunan? Any idea? What does it mean? It's Basil here? What? Okay, what do you think? What does it mean by stoic of the main reaction? Not sure. How about Naveen? Naveen here no? Oh, okay. Yes, correct. It's about the minimum ratio that you need. When you have your reaction, for example, I give you fuel and combustion example lah, easier. Okay. For example, for combustion, you have this and this. Okay, so you need to balance up the equation at start. We know from combustion, this is the products. Okay, how do you balance up the equation? How much of O2 that you require? Try to balance out the equation. Still remember how to balance the equation? How much of O2 that you need? 2? 3/2. Right? Two. 2 of O2? 4. Then here only 3. How many O2 you require? 2. Okay, 2. Then H2O. Okay, this one is just a simple equation. Now, this is at start. At start, meaning that the minimum amount from this equation, okay, the minimum amount of O2 you required for the fuel to react to produce this amount of product at start. Okay, so you should balance up your equation of your process. Why it is important to know the minimum amount in order to produce your product. If let's say you don't know how much of O2 that you need, then your CO2 perhaps cannot be produced at your targeted amount. Okay, so you need to get the correct stoichiometric equation first. From there, you can identify 1 mole of methane react with 2 moles of O2. Okay, if you put, let's say, you do it wrongly, you say you put 5 mole O2, you will still have the product, but then you have excess of oxygen, which the design of your equipment, perhaps your compressor will have large size of compressor. Instead, you only need a compressor that can supply 2 moles only. It's a cost to be borne over there. Okay? Get the idea? The terms of stoic at the main reaction pathway. This one is a simple one. Haven't considered any catalyst yet. Okay? Okay, then the major purpose of this section is to investigate the input and output structure of the process. Input-output, again, your raw material and your product. Output product plus byproduct plus the waste. Okay, input here can be your feed, catalyst, if required. Okay. Okay, so this input-output can be represented in this way. Process concept diagram, then the structure of the process flow diagram, then only you can generate the BFD, block flow diagram. At first, the process concept diagram. Input, your raw material, product. Then you detail out a bit the process flow. Then only you come up what are perhaps the reaction, the reactor you need, separation, you need the distillation column. Okay. Okay, example we have here, toluene hydrodealkylation process. Concept diagram represent the most basic of the process. Okay. So from here, you have the PFD already. Concept diagram is the blue color one. Okay, where we only covers concept diagram. You don't specify the rest yet. Your input, okay, and your output. The utility, not yet, for the process concept diagram. Okay, you want only the concept first. Then after the concept diagram, you can generate the flow diagram, process flow diagram. Okay, process flow diagram, perhaps here your raw material, then here combustion process, separation. Okay, here separation. Okay, then only you generate the BFD. More details than the PFD. What do you need? How many of the unit odd that you require? Okay, so these are the details of the input-output structure of the process. You need to consider the feed purity. Let me make it bigger. Okay, feed purity and trace the component. Feed stream entering a process do not contain pure chemicals. So what you should do you need to purify the input or not? Okay, should purification step be performed? Okay, some useful heuristics. You can use inerts. Okay, if let's say your input is not pure, you can use inert. One of the heuristic, the alternative, the shortcuts. Okay, inerts, where inerts do not react with the reactions. Then if the separation of impurities is difficult, do not separate. For example, you have a zeotrope solution, water and ethanol, where we know water boiling point is 100 degrees C, ethanol is how many? 70, 72, 80, roughly 70, the boiling point of ethanol. Okay, so we call that as azeotrope because their boiling point is close. Hard to separate. You need few series of distillation, ordinary distillation column, or you need few stages. Okay. That's why one of the choice is do not separate them in the beginning. Third, if the impurities fall or poison catalyst, then separate them. Okay, for example, if you have sulfur in your input, you need to separate the sulfur. Because sometimes if you don't separate, sulfur will react with your other inputs or react with your other chemicals to produce perhaps hazardous gas, okay, H2S or SOS. Okay, then if impurity reacts to form difficult to separate material or hazardous product, then separate it. If the impurity is present in large quantities, then you can opt to purify the feed. Okay, I will share with you one example of I think final exam question. related to this. It gives you a case study, then you need to decide whether which method to be used. Do not separate or separate it. If separate it, how? Okay. So next step is to stabilize the products. If the product stream is for reactive or unstable, then additional stabilizing chemicals may need to be added before it goes to storage. Okay, if your product is reactive or unstable, you need to add in something to stabilize it. Or you need to perhaps change its phase to stabilize it. Okay, these stabilizing chemicals are additional feed streams to the process. Additional feed stream here means once you have your products at the end, okay, this is your process. You have your product to go to the storage. Then you have additional stream, stabilizing chemicals. Okay, here, stabilizing chemicals, which you need to consider the design as well of this storage. The piping, the size of storage tank, what is the condition, temperature, pressure, and what are the materials for the storage tank? What are the materials for the piping system? Is there any controller need to be installed? Okay. Okay, third point is inert to can control exothermic and equilibrium reactions. Okay, if you have exothermic reactions, how you want to control it? What is exothermic reaction? Huh? Release of energy, release of heat. So certain process, it release too much heat that you need to control it. How to control it? Perhaps you can add in some inert, or you can add in, you can supply chill water to cool down the temperature, or refrigerant, or you can supply it to heat exchanger network to help with the energy. Okay, here it mentioned in some process, enough steam or other inert stream is added to move the reaction mixture out of the flammability limits. Okay, perhaps you need to add inert to control the temperature. Steam is fed to the reactor to dilute the feed and provide thermal ballast to absorb the heat of reaction and make control easier. So the steam provide to dilute the feed, reduce the concentration, and provide thermal ballast to absorb the heat. So the steam, water vapor, it can absorb the heat, help to reduce the energy a bit. Okay. Okay. Okay, last one on step 2. Last one. Step 2. the last slide. Still input and output. Okay, these are the things that you need to consider. The basic economic analysis. Okay, what are the chemical components that will enter your process and leave as product? All direction, desired and undesired. You must practice some basic economic analysis. Let's say your product, what is your market price for product? Then what is the market price for your raw material? Compare the profit margin. How much? Is there any loss? Will you gain or you lose if you use that raw material to produce that particular product? Okay, so profit margin over here, value of the product minus cost of the raw material. For example, the VCM, you have the products is HCl and the VCM. Okay, the feed is ethane and chlorine. So this market price of the product minus the cost of the feed. Is there any cost or not? Profit or not? Okay. For example, this is just a number. For example, VCM is 1,000 per kg. Per kg, 1,000. HCl, if you sell, then let's say 500,000 per kg. RM, for example. So product wise 1.5K. Let's say you buy your ethylene 200 per kg. Chlorine gas perhaps 500, sorry. Not that expensive. 300, for example lah. Okay, per kg. So feed here, you have total of 500. Your cost is 500 per kg. Sorry, 500 per feed. Your product is 1,500. This is your product. So the profit margin 1,500 minus the cost 500. You have profit of 1,000. This is the basic one lah. Product minus cost. Not considering the utilities, the equipment yet. The basic economic analysis. Okay. So if the basic you see there are profits, then you can proceed designing the process flow, everything. If the profit margin analysis over here, there is loss, don't bother to proceed with the process. Okay, you won't get any profit from that. Okay, because certain chemicals used in the feed is costly. Okay, that's why in the feed over here, you need to choose wisely what are your raw materials that can bring profit to your process. Okay. Okay. We stop there. This one is step 3. Step 3, we continue tomorrow. And I'll share with you, we will discuss some final exam question tomorrow. Okay, so that's all for the lecture. Any question before we stop? No question, thank you. For those who cannot scan, write manually, yeah? Write your attendance over here.
Let's start the research.
Yeah.
Yes. Then
So I will add 3 of you. If I be student mine as a student in the WhatsApp group, then I will write what are the templates.
technically you will keep the record.
You write your name here. Student 8. You also. For the midterm, what's that time? 19. I'm going to Vietnam. When you come back again, and then when you come back? Huh? 22nd. Yeah. Already buy the ticket? Yeah, what did I do? Okay. Do you think we can send an email to the yes. Proof of, yeah, proof of the tickets. Yeah. Oh no.